Vladimir, you can start, please.
I think so, okay. So now it's time is coming, okay. So hello everybody, we have a talk. So it's my pleasure, very big pleasure, so to speak. Okay, so to introduce Professor Hans Cuypers from Eindhoven University of Technology, Netherlands. So he will talk about simple groups, or excuse me, simple algebras and their automorphism groups. And the title of the talk is Every Group is the Automorphism Group of a Simple Algebra. Some follow-up after Popov and Gordeev theorem. Go ahead, Hans.
Okay, thank you very much. Thank you for the invitation. And let me first try to share my screen. Let's see. So is it visible for you? Okay. Then, yeah, this is my title. Every group is the automorphism group of a simple algebra. And as was already said, this is an old problem 30 years ago. Popov asked the question, is every finite group the automorphism group of a finite dimensional simple algebra? And a few years later, the first positive answer was given by Popov and Gordeev. And they looked at this problem in the context of algebraic groups and proved that every algebraic group is actually the automorphism group of a simple algebra. And there was a little bit of a restriction on the size of the field that should be big enough. In somewhat more recent times, there have been two papers on the automorphism group of an evolution algebra. And the first, in at least as far as I could figure out, in 22 was by Sriwangsa and Zhu, where they show that every finite group is the automorphism group of an evolution algebra, provided that the field is of characteristic 0. But around that same time, also Kostoya and co-workers, they looked at the same problem and they showed that each finite group is the automorphism group of an evolution algebra over a field.
We don't see the last line, so perhaps you can switch to some full screen mode or something.
I had it in full screen mode, so.
Okay, so maybe it's too long. Okay.
Yeah. Do you see now the last line?
Yes, the last one.
Yeah. Well, then the transitions are maybe not as nice, but we will see. But again, in this paper, there is also a restriction on the size of the field. It should be at least twice the order of the group. And today I want to discuss our theorem. And that says for every group, doesn't need to be a finite group. It could be also a very big infinite group. And for every field, so no restrictions on the size of the field, there are infinitely many simple algebras such that this group is isomorphic to the automorphism group of the algebra. And the algebras that I construct in this talk, they will be defined over a field F. But if that field has at least 4 elements, we can make all these algebras commutative or non-commutative, whatever we want. For the field with 3 elements, that might be possible. I still have to figure out. But for the field with 2 elements, our methods will always give a commutative algebra. And of course, we also want these algebras, well, they are simple, but we also want them to be finite dimensional. But that only works if the group G that we start with is a finite group. So our approach doesn't need actually any real conditions on the field, except it has you want to have a non-commutative algebra, then you need at least 4 elements. All these algebras will be non-associative. So that's our answer, and as you can imagine, as in many cases in this area of mathematics, Vrucht's theorem plays a role. And that's one of the starting points actually of also the proofs given by the people that worked on these evolution algebras. They also used Vrucht's theorem to prove that there are infinitely many algebras with these properties that we want, starting with some group. Well, what does Vrucht's theorem says? Well, it says if you take any group, then there is a connected graph delta such that your group is isomorphic to the automorphism group of delta. Vrucht proved this theorem already in 39 and extended it a bit in 49, but there are also extensions by de Groot and Sabidusi that prove that this theorem is also true for infinite groups. So the starting point for Vrucht and also the two theorems on evolution algebras are graphs, and that's also where we start. However, in contrast to what Vrucht is doing, we start with a directed graph. And this directed graph that has directed edges, no loops. And for such a graph, we label all the edges with some element from the field. Well, of course, if the field has only 2 elements and the label should be non-zero, then there is only one choice. But as soon as the field has more elements, then we can label the elements with the edges with more elements. In particular, if we have a directed graph, we can label an edge from x to y with an element alpha, and the other direction from y to x with a different element. And that is the method to get non-commutative algebras. Well, how are our algebras defined? Actually, this graph gamma is the multiplication table, or encodes the multiplication table of our algebra. We start with the vertices of our graph as the basis elements, and we define the product for 2 vertices x and y as x times y is x if x and y are equal. It's 0 if there is no edge on x and y, and otherwise it's alpha times x plus y, where alpha is the label on the edge. So
előadást hallgatok, de nem zavarsz, mert le vagyok alszva.
Excuse me? I heard a question, but sorry, I couldn't understand.
If you want, you can. Okay, I didn't hear.
Well, okay. So this is definition of our in order to look into these algebras, we want to make first some observations. Every basis element x, which is a vertex of our graph, satisfies that x squared is x, so you have an idempotent of your algebra. And the algebra is commutative if and only if the graph that you start with is symmetric. That means if there is an edge from x to y, there's also an edge from y to x, and the labels are the same. In particular, also, if you have an edge, then the algebra will be non-associative. And the last remark, which is of course of importance for our construction, is that if you look at the automorphism group of the graph, and then I mean the automorphism group of the labeled graph, you find a subgroup of the automorphism group of the algebra. Yeah, it induces, of course, a permutation of the vertices, but the product is also invariant. So that's a first observation. And yeah, we want to prove our main result. That means we have to figure out which of these graphs do give us an algebra which is simple. And the second question, we want to show that starting with a group and a graph and having the automorphism group of the graph, that the automorphism group of the algebra is maybe equal to this group of automorphisms of our graph. And then the final question is, of course, can we find for each group a graph, such a directed graph that we have in mind, such that the automorphism group of that graph is the group that you start with? So these are the three questions that I would like to answer, and together they will give us a proof of our main result. First of all, simplicity. Well, I will not go into the proofs here, but I give you two situations in which there is an ideal in our algebra. And the first situation is that suppose you do have two vertices x and y, such that they are adjacent, and the edges in both directions have the label a half. Well, you furthermore, every vertex which is adjacent to x is also adjacent to y, and vice versa, and that the labels are the same. So if the edge xz label alpha, then so does the edge yz. And similarly for the edges in the other direction from z to x and z to y. Well, in that case, completely the same role. So if you identify them, you get a new graph because all the labels on the edges going from x and going to y have the same value. You get again an algebra of the same type, but you get an algebra in which you have identified x and y. So in that way, you can at least have the idea that such a ideal does exist. The second way that an ideal can arise is the following, and that's the case where our graph is a complete graph on a finite number of vertices, and complete means any two edges that you can think of exist, and all the edges have the same label, which is 1 divided by 2 minus n. Of course, it means the element that is the inverse of 2 minus n in the field. And then the sum of all the vertices will span a one-dimensional ideal. This case has been already considered by Harada and Allen in, I think, the end of the 80s or in the 80s, where they looked at algebras that are related to two transitive groups. And especially if n is divisible by the characteristic of the field, they found Jordan algebras satisfying this setup. But then there is this one-dimensional ideal. So our first theorem towards our main result is the proof, is the theorem here that tells us that our algebra is simple, or algebra that we obtain from a graph gamma, unless we are in one of the two situations that I described before. So either you have two vertices x and y that you can identify, and you get a quotient algebra, which has the same structure, or your graph is a complete graph and all the labels have a very special value. But that, of course, already gives us a lot of freedom, because these are very particular situations that we can easily avoid if we are looking at the arbitrary graphs. In particular, if we have a graph, let's say it's symmetric, that means any edge xy, there's also the edge yx. And in the underlying graph, where you forget about the direction of the edges, there are no 3 cycles. So that means the girth of the graph is at least 4. Then you will end up with a simple algebra. And this is something that we will use later, or the graphs that we will consider will be graphs which will be symmetric directed and have girth which is at least 4. So that is the first problem which we have solved, more or less. Simplicity. Most of our algebras will be simple. But the other question, which is maybe even a bit harder to answer, is one is the automorphism group of our graph equal to the automorphism group of our algebra? Of course, we have already noticed that the automorphism group of the graph is a subgroup of the automorphism group of our algebra. But why is it not much bigger, the automorphism group of the algebra? So we can rephrase this a little bit. If you take an automorphism G of the algebra and you fix a basis element x, what is then the image of this x under this automorphism? Is there a way that we can conclude that the image of such x will be again in x, will be again a basis element? Well, that's what I want to find out. I want to find some properties of the elements x such that I know these properties will be invariant under the automorphism group of the algebra, but they characterize the elements in my set x, because then I know that the image of a little x will again be an x. So I have to find some properties of these basis elements which are vertices of my graph. Well, here is a list of some of the properties that will be very helpful. First is, of course, if you take a little x in your set x, I already noticed x squared is x, so I have an idempotent. And if you look at the labels, these labels turn out to be the eigenvalues of left multiplication or right multiplication with x. So if none of the labels is equal to 1, then such x is not only an idempotent, it's a primitive idempotent. Its eigenspace just equals the one space spanned by x. The other observation is that I can also relate left multiplication by x, L of x, and find out what is the rank of left multiplication with x. If you think back of the definition, every element y which is not adjacent to x will be mapped to 0, and every element y which is adjacent will be mapped to alpha times x plus y. X itself is already in the range of L of x, so y is also in there, and I get that the rank of such an element, left multiplication with x, is equal to 1 plus the out degree of x. And by the same arguments, the rank of right multiplication with x is equal to the 1 plus the in degree of an element x in my graph. So these are 3 properties, or maybe 4 if you consider being primitive an extra property, that are of course invariant under the action of the automorphism group of our algebra. And that's what we will use to characterize the elements in X. To do that, I will make use of the support of an element A in A. Now my element is not necessarily an element from X. No, it's an arbitrary element of my algebra. But my set X is a basis of the algebra, so I can express my A in this basis. And then the support of A is just those elements from X for which the coefficient lambda sub y in this expression is non-zero. Since every element is a finite sum of scalar multiples of basis elements, I do have that the support of A is a finite subset of the vertex set of my graph. And now I can also see it as defining a subgraph, or when I just forget about the directions, a subgraph of the underlying graph. So that's the support of an element. And our multiplication is, well, it's a very easy multiplication. So where am I here? Sorry. So I can look at what happens if I take my A and I multiply it with some element X. Well, two things can happen. My X can be an element from A, and multiplying with X will kill all the elements which are not adjacent to X. So X times A will have a support which is contained in A and only contains the neighbors of X and a linear a sum of scalars times X, but that means X could be in there or not. Could be that the sum of the scalars that come in front of X are 0. So this support of X times A is just the neighbors of X, maybe together with X or not. Similarly, if I take X outside, you again have the neighbors of X in the support of A, they will survive. And maybe X will survive for the support of X times A. And of course, multiplying from the right will give you a similar picture. But this property helps me in finding some lower bounds for the support for the rank of left multiplication by A or right multiplication by A. Well, in particular, if A is an idempotent, then each connected component of this support will be, if you look at A squared, will be again that same component. So each component will be an eigenvector for the eigenvalue 1. In particular, if A is a primitive idempotent, you know it's connected, it only has one connected component and is a connected subgraph. The other observation that is that if there is a minimal cycle of length at least 6, so the Gers is at least 6, then if the minimal cycle of the support of A is at least 6, then left multiplication by A or right multiplication by A will have a rank at least 4. And also if the support is a tree with diameter at least 4. Well, let me just give you a proof of that fact. Well, in both situations, you will find a path x1, x2, x3, x4, x5 inside the support, but because the girth is at least 6, there are no extra edges between these points. There might be more points in the support, but these are there. So if you multiply x1 with a, then x1 and x2 might be in the support, but not x3, x4, and x5. If you multiply it a with x2, x1 and x3 will be in there, maybe x2, but certainly not x4 and x5, and so on. But that means that this support, well, it contains x2, but not these elements. It contains x3, but not x4 and 5, x4 and not x5 and x5. It has at least dimension 4. And therefore, L sub A has rank at least 4. Now I have to switch a few slides because it doesn't work. And of course, this argument works if the girth is at least 6, or if it's a 3 with diameter 4, because then you have this situation. But the same argument also shows you that if the support is a 3 and the diameter is maybe not 4, but a little bit smaller, then there will also be a rank of left multiplication by a of at least 4. Well, here is actually the picture in that case. We would have x1, x2, x3, x4, same arguments as before, giving us at least a dimension 3 for, say, the rank. But points y1 and y2, which are just outside of that support, give us again 2 extra dimensions. And we will see that if the diameter is at least d, then the rank can be shown to be at least 4. It's a bit of technical things, but it shows us the following proposition, which is very close to what we want. If you have a connected graph and it's a symmetric directed graph and edges have vertices of degree 2 and 3, and one the vertex of degree 2 and the other of degree at least 3, labels are different from 0 and 1. So my field has at least 3 elements. The field with 2 elements is a bit more complicated, but I will not go into that proof. And if your graph has a girth of at least 6, then if you take a vertex of degree 2 and you take an automorphism of your algebra, then the image of that element x is an element, let's call it A. It has rank, left multiplication with A has rank 3, but the fact that the labels are different from 0 and 1 means that it is a primitive idempotent. So my arguments, they show it's a primitive idempotent, therefore the support is connected. Left multiplication or right multiplication have rank 3. That means the support cannot have a cycle, because the cycle would have at least a path of length 5, and then the rank would be 4, at least 4. But then it's a tree, and in the tree I argued, yeah, the diameter cannot be big because you can use the vertices outside to get a bigger rank. So it will have a support of size 1. However, it's an idempotent, so a squared is a. So if its support has size 1, it's just a scalar multiple of an idempotent, but then it has to be this idempotent. Yeah, if you have a scalar multiple of your idempotent, then that scalar can only be 1. to make it idempotent.
Just stipulations to get the last conclusions that each vertex element, so it could be some idempotent. You use something about its size, or so how to know that it's exactly a vertex, not any idempotent, but just a vertex. Can you just
Yes. So if I look at this A, it's an image of a primitive idempotent, so itself a primitive idempotent. But means that the sort is connected, because every connected component would be another eigenvector for the eigenvalue 1. The other one was X had only 2 neighbors. So it's the rank of Lx is 1 plus 2 is 3. And therefore also A, L multiplication by A, left or right, will have rank 3. And in the support of A, if you would have a path of length 4 or 5, then I tried to prove in the previous slides that the rank would be at least 4. So that's not allowed. So my conditions, I have no path. That means the diameter of this support is just 0 and it's a single point. And therefore it's a scalar of some y, but it's primitive idempotent, and therefore it has to be equal to that y, which is also a vertex from my graph X. Yeah, so hopefully that's making it a little bit more clear. And that means that we do have what we want, namely that any automorphism stabilizes our set, at least some vertices of our set X. So, but which graphs can we now use? Because I said, well, my graphs, they should be symmetric directed graphs. That's what I used in my arguments. They should be labeled without zeros and ones. Well, in that case, if I want to have ones, I have to give some more arguments. But I also want that given a group G that you start with, that G is the automorphism group of your graph, and that on each edge we find a vertex of degree 2, which was the X that I used, and the other ones should be of degree bigger. And then finally, these graphs, they should have a big girth, well, at least 6. So they have no small cycles. And actually, there is a class of graphs that does this. And that's what I call the directed incidence graph of an arbitrary graph delta. So I start now with a different graph delta, and I construct a graph X that satisfies these properties. What do? I take the vertices and the edges of my graph delta, and they together form the vertex set of my new graph. And as edges, I take the pairs, a vertex and an edge, such that the vertex is on the edge, or the direction in the other way is the edge vertex pair. This kind of graph, well, it comes also from geometry, where it's just the incidence graph of the geometry, but here the graph delta is a geometry in which is just a graph, ordinary graph with lines being the edges. So what are properties of this graph? Well, if your original graph delta is connected, then the directed incidence graph will also be connected and being symmetric. Vertices on some edge, well, a vertex of my new graph is a vertex edge pair of my old graph. The edges will have only 2 neighbors, and the vertices have at least 3 neighbors. So it's indeed that the vertices of my gamma that are on some edge have degree 2 and degree at least 3. Any 3 cycle in my original delta will become a 6 cycle in my new graph gamma, because you have to move from vertex edge to edge vertex to and so on. You double the girths, and delta has girths 3, at least 3, therefore gamma has girths at least 6. Clearly, we can also reconstruct delta from gamma. It's not so hard to see. Degrees 2 vertices of gamma are the edges. Degree at least 3 vertices are the vertices of delta. So we can reconstruct delta from gamma, but that implies that their automorphism groups are the same. And now we can label the edges with elements from our field, just the way we want. And we can even have opposite edges have different labels without ruining that the automorphism group will change. We just give a constant labeling to each orbit of the automorphism group. But the vertex edge pair will never be mapped to an edge vertex pair. So one direction will not go to the other direction. And that means the automorphism group will stay the same, and we can get the nice labeling the way we want it. So that means if we have such a directed incidence graph labeled by these elements, that the automorphism group of the algebra will also be the automorphism group of our graph gamma. Why? Well, maybe we should start here with the second paragraph. If you have a vertex of your delta, so a degree 2 vertex of our new graph gamma, then any automorphism of our algebra will map that element again to a vertex of our graph gamma. That was my previous proposition. The only thing is that I also now have to look at those vertices of gamma which come from not from edges of delta, that come from vertices of delta. But such vertices, they are on at least two edges, the intersection of two edges, but that these edges, they are mapped to what we want. And if you look at the range of multiplication with these edges, then your A should be in the intersection of the images. And you can, of course, do some little work there, but you can find that also for the vertices of delta, so the elements of gamma which have degree at least 3, that they are also mapped to vertices of gamma. So that gives us that all the elements from our set X will be mapped to the set X, and our automorphism of the algebra will induce an automorphism of the graph. Well, as I already said a couple of times, our result is also true if the field has two elements. And in that case, all labels are 1, but it requires some extra work because I used here that the support of a idempotent is connected, but here we have to do a little bit more work because it can be that it could not be connected, but similar techniques will work there, and we can prove that. So we are almost done. We only need the right version of Vrucht's theorem, namely we need Vrucht's theorem for directed incidence graphs. But a small variation of Vrucht's theorem, or better say the Groot and Sabidusi's extension, prove the result. So if we take any group, it doesn't matter whether it's a finite or infinite group, then we can find infinitely many connected and labeled directed incidence graphs with automorphism group G, where some of the vertices have degree 2 and the others have degree 3, because it's coming from an incidence graph. So those observations together with this theorem shows us our main result. You can take any group and you find infinitely many labeled directed incidence graphs gamma with G as automorphism group. Then labeling them such that on G orbits the labels are constant, you still have G, the automorphism group of the graph. And you can do this labeling in such a way that edges from x to y and y to x have the same value or not. Of course, then your field to have at least 4 elements. I don't want to use 1 as a label. And then this group will be the same as the automorphism group of the algebra that we construct. So there are infinitely many simple algebras, A sub gamma, such that G is the automorphism group. Depending on the choice of your labeling, it will be a commutative or a non-commutative algebra. And for the field with 3 elements, well, it could be that if we allow labels 1 and -1, that we can do the job, but I didn't care to figure that out. So that's, but this proves our main result. Of course, in this case, in this talk, I really restricted to the minimum conditions that we need the gers of a graph to be at least 6. One vertex on an edge having a degree 2, the other having degree at least 3. Well, the arguments are, of course, a little bit stronger, and the method can be refined to include more graphs. The main thing is that you need some small valency and some big gers to apply our methods on the support of an element A, which is the image of such an X. In particular, we, instead of incidence graphs of graphs, we can also use incidence graphs of partial linear spaces with 3 points per line. And there is a variation of Vrucht's theorem for Steiner triple systems that also does that. So we can use that version of Vrucht's theorem for Steiner triple systems and use the incidence graphs of them and get similar results. Another way of looking at this is that, well, you may have a very nice group which is defined as the automorphism group of your favorite graph. And then you just take the incidence graph of that graph and apply our methods. Then, of course, you don't need per se that you have Vrucht's theorem to produce many of them, but you have an interesting situation. And last remark here is that our algebras, well, they are generated by the elements X, which are idempotents, and then very often are primitive idempotents. So our algebras are also axial algebras. Let me give you some interesting examples. For example, the Hickman-Sims group is a sporadic simple group that is constructed as the automorphism group of a graph with 100 vertices, a valency 22. So our method gives us for any field F a 1200 dimensional algebra with the automorphism group isomorphic to the double cover of Hickman-Sims. In a similar way, the Hall-Janko group, that's also defined as the automorphism group or contained in the automorphism group of a graph with 100 vertices, but in this time valency 36. And our construction gives us a 1900-dimensional algebra that has the double cover of Hell-Yanko as its automorphism group. And also the McLaughlin group we can use. And the McLaughlin graph on 275 vertices yields then a 15,675 dimensional algebra. All these algebras are also, as I said, axial algebras. So I don't know whether you know what an axial algebra is, but let me give you a very short overview. It's a pair consisting of an algebra A and a set script A, where A is generated by the elements in script A, and these elements are primitive semi-simple idempotents. And the special thing about axial algebras is that they satisfy a fusion law. And a fusion law is nothing more than a map from a finite subset of a field F times itself to the subset, to a subset of these elements. And what you want is that if you take such an idempotent in your element A, then the spectrum of left multiplication or right multiplication, I have here a commutative algebra, is contained in that set F. And the fusion rule tells us how the eigenspaces A sub lambda of A and A sub mu of A, how they multiply. The product of these two eigenspaces will be contained in the direct sum of the eigenspaces where rho is running over lambda star mu, which is then the subset of 2 to the power f. And we call an axial algebra of type star if all the x's in this script A do satisfy that law. So our algebra, if we fix all labels with by one element alpha, not 0 and 1, they will produce an axial algebra that has as fusion law the table given here. So the three eigenvalues are 1, alpha, and 0. And alpha times alpha, for example, will give the set 1 comma alpha. So the eigenspace of alpha times the eigenspace of alpha will come up in the eigenspace of alpha together with A itself. And in that way, you can think of that. So our result also shows that axial algebras actually can be constructed, and there are tons of them, even with a quite simple fusion law as given here. In particular, for any finite group, there are infinitely many even simple axial algebras that are of the type as given in the table, with G as the automorphism group. And that complements the result of Spektorov and his co-workers that say, if you have a finite-dimensional commutative axial algebra and a half is not in your set F of eigenvalues, then the automorphism group of A is finite. And our result shows that we always can find an axial algebra, even with only 3 eigenvalues for the elements in the idempotents, such that the fusion law is this diagram. Okay, this is the end of my story. Thank you for your attention. And if there are any questions, please ask them.
Oh, many thanks, Hans, for a very interesting talk. Yeah, certainly there should be questions. Okay. First, I deliver it to auditory. Somebody would like to ask something or comment? Mhm. Let me just start. Okay, so I have several questions, maybe to reduce the number. Okay, first of all, the original proof of Popov and Gordeev was, if I'm correct, pure algebraic geometric, and you have completely different. So it's not just a generalization; it's just completely different stuff, so to speak, right?
Yes.
So,
Completely
and this
different.
Frucht's theorem is like the bridge between graph theory and automorphisms and finite groups, and certainly you have another bridge between graph theory and you construct an algebra by it. Okay.
Yes, it's yeah. I think the main thing is that the definition of the algebras and the way that I can identify special elements like idempotents with a low rank of left multiplication by them, and that's the main tool that we use.
Yes, and can one think that in that case, these produce, in a sense, the smallest possible. Okay, I don't know how to say. Okay, so the proof by Popov is completely different. So it's like existence proof. Okay, in a sense. And that's why maybe some restrictions by the field's characteristic. You don't have any. Yeah, so one can see, just don't work with field so much. Okay. By the way, this 1/2 on the first slide, when you mentioned with order 4 something, you mentioned that it was in the context of ideal, that if there are no edge with 1/2, then something happens. Does it mean that this left multiplication operator doesn't have spectrum 1/2? So by idempotent, this is exactly 1/2 appearing.
If there is an edge with value alpha, then alpha will be an eigen value. So
one of eigenvalues of this.
Yes, one of the eigenvalues, of course, but you can use a lot of alpha. So, but if you use alpha as a half, that means that a half is also an eigenvalue.
So I will you confirm that it's special in some way, or
yes,
yes,
it is special.
And this table on the screen right now, so it's completely different. Okay, it's smaller or it's easier, so to speak, than normally fusion laws for.
Actually, yes, yeah. If you use a lot of labels, it will be a very big table.
The point is, you can control idempotence, but you can decrease the number of fusion laws or values. So you have only one non-trivial alpha right now. Okay.
Yes.
So, for instance, monster group could be obtained in this way, or
everything works more or less for this alpha, because for axial algebras you want the algebra to be commutative, so you only need one alpha, and that's and then it works. It doesn't matter which alphas you use.
Okay.
Yeah. Actually, you can also see if you have an axial algebra with this table, and you know that any two idempotents span a two-dimensional subalgebra, then it has to be from this construction. So this is very minimal. This is the smallest algebras that you can think of. That's.
And my last question, maybe somebody also. You mentioned the Steiner triple theorem and analog.
Yes.
Is it analog you proof, or it already in the literature? What do you mean?
It is in the literature. I think Bill Cantor proved some results in this respect, that every group is the automorphism group of a Steiner triple system. Mendelssohn did, I think, the first proof in this direction, and so you can replace Frucht's theorem by that theorem, and then because lines have only 3 points, the problem will be I have elements with left multiplication of rank 4, and the arguments still work.
Yeah.
But it becomes a little bit messier than the proof. But
okay, yeah. So it's Very original idea. Okay, so and very nice to follow up. Okay, so again, okay, somebody have some questions or comments? Okay, Ivan, please.
Thank you very much. Thank you for a very nice talk. In fact, I had two questions, but first was already asked whether it's possible to reformulate Gordeev-Popov construction in terms of graphs, but it seems that the answer is no, so it has nothing to do with graphs, right?
No, they look up at the algebraic groups, and they consider the action on tensor products of vector spaces, and they identify then stabilizers. Well, you know, a tensor product carries some algebra structure then also, and that way, and so they just prove the existence then of some algebra that they can show to be simple. But to be honest, I don't understand the complete proof. But
no, I remember that at that time I understand when it was just published. I understood.
Okay.
But it was a generalization, not generalization, but parallel or direction of research. Consider not algebraic groups, but algebraic semigroups, algebraic monoids. And it was a paper by Alexander Perepechko, I will put it to the chart, that any affine algebraic monoid may be realized as a monoid of endomorphism of finite-dimensional simple algebras. So maybe theoretically this way we can obtain fine semigroups which are endomorphism of such algebras. So I don't know whether this is reasonable, but
yeah, I also do not know, but actually I hardly use anything about the group except for that you have the group as the automorphism group of some graph. And doesn't matter which group it is, it doesn't matter which graph it is, but from there on I can just have this connection between the graph and the algebra. So it might be that if you look at the endomorphisms that you have a similar way to do that. But if you can put that reference somewhere, then I might have a look at that, yes. But the fact that, yeah, the group doesn't play a big role in the proof. You know.
Okay.
Other questions? Or okay. Mm-hmm. So, yeah, I believe this alternative proof is certainly important because it's at least for my point of view, it gives some intuition how to get these automorphism interpretations. Okay, maybe I need to work out something about simplicity ideals. So yeah, this is very short proof, but presentation. But it should be published or it should be available after a while, or what is okay?
Yeah. So as I said, I hope I get the message
because
next
such
week.
a proof is needed, so to speak. Okay, so it's very interesting that it is, and this table is just give an impression that maybe fusion laws by their own could be interesting, but in fact you can reduce it to some smaller counterpart which gives the same, so to speak, automorphism group. It was unexpected from my point of view.
In a way, it's also a little bit disappointing because even for such an easy table, there are zillions of examples. So
no, okay, so it's certainly so. Okay,
but it does mean that you have to if you look at axial algebras, you have to give
you have many cells.
A nice fusion. You have to have a good fusion law to be able to say something, and otherwise there are too many examples.
Okay. Yes. Yeah, okay. So if there are no other questions, I would like to thank Hans again. So for very interesting talk. Okay. Thank you again.
Well, thank you.
So the seminar is finished, and next one will be announced. Okay.
Okay. Goodbye, everybody.
Bye.